Hi, I'm Ed Byers, and this is an introduction to the models and framework that were used in the RE and RE4AFAGRi research projects. The RE4AFAGRi modeling platform is a multi-model framework, helps understand and analyze deficits, requirements, and optimal solutions for the integrated water-energy land nexus, with a specific focus on developing countries, and was developed specifically with sub-Saharan Africa in mind. 4 models are representing this water, energy, land, food nexus, and these are water crop, MLED, onset, and the message or nest model. These are both calibrated and soft linked through the RE4AFAGRi platform, and together really helpful for helping understand how best to achieve sustainable development goals. First up is the water crop model, which is an evapotranspiration model that helps estimate the demands required by crops. Normally, we understand this in terms of rainfall requirements and the soil moisture in different locations where agriculture is being done, and this varies from crop to crop. But we can also use it to understand how irrigation, providing more water, can help increase yields. And this is what we call the yield gap. It takes inputs through time, including precipitation and temperature time series. It can also be used to account for changing yields and water demands for under climate change scenarios. Critically, it can help us identify what are the investments required to boost yields and improve the livelihoods and businesses of farmers across Africa. Next is the MLED model, multi-sectoral latent energy demand. In many places, people don't have access to reliable electricity, or not as much as they need or as much as they can afford. Next up is the MLED, multi-sectoral latent energy demand model. In many places across the world, particularly in sub-Saharan Africa, people lack access to electricity and energy sources, or are unable to afford as much as they would like to use. MLED helps us estimate what the actual potential energy use could be if this energy was available across different types of uses, including residential, business purposes, agriculture, irrigation, and so forth. It combines really high resolution spatial data, big data, and also bottom-up energy modeling approaches so that we can map those demands for the different uses across the country. But it also combines detailed temporal resolution, because it's really important to understand how these demands will change during the day. And this is important for grid planning and ensuring reliability of the electricity system, which we know can be a big problem in many countries. To support in that effort, the open source spatial electrification tool supports country-level electrification planning also to meet electricity access goals, helps us understand what are the investments required, what types of electricity systems should be developed in different places. This can depend on a large number of factors, such as population density, fuel prices, and distance from roads and distance to the grid. It also combines many spatial datasets and brings these together in a GIS-based optimization tool. Ultimately, it subsets the different types of grid and transmission infrastructure that should be provided in different locations, whether these are very small-scale grids, likely to be in very rural areas far from populated centers, or whether it should be more traditional grids and connect to the larger electricity network. This would be more suitable for industrial and heavily populated areas. This is an example from Zambia, from this project, and here we see the different colors. The blue areas are where it's recommended that the traditional grid transmission is extended, because these are the more populated places. The green areas include solar hybrid mini-grids, and these are smaller community-based places. And then the yellow areas are probably the least populated areas, and also probably the most expensive to provide normal transmission infrastructure, where the model recommends standalone solar island networks. Lastly is the Nexus Solutions tool. This brings together the traditional energy systems planning model called MESSAGE breaks it out into regions for the specific country and incorporates other water and land-based information. For example, river basins can be represented, and there's a water model that understands and tells the model what are the water resources available within those different regions for providing water access, in particular irrigation. It also takes information from water crop, from the land use and food production. But ultimately, it helps optimize through the long term, across multiple decades, what are the necessary investments, typically, for example, for meeting the SDGs, but also climate goals. NEST is an integrated model that brings together many data sets and provides investment pathways for sustainable transformation. In order to get using these models, the code, the data, and documentation is all brought together on the RE4AFAGRi.Africa platform. We've included the data, including inputs and outputs from the analysis done for Zambia. The codes are available on GitHub and can be brought together in the modeling platform using the data bundles. And we've also provided documentation to help guide you through it, in addition to other videos that follow this one, which go into much more detail about the models, both in how they can be used and how to get them up and running. Thanks for your attention. And if you have questions or need help, we'd love to hear from you.